Here's a problem with 3-point charges, and they are arranged along the circumference of a circle, and they want you to calculate the resultant electric field at the origin. So when you just look at it, there is a good deal of symmetry here, so it's actually, it ends up being an easier problem than most. If you're imagining drawing the electric field at the center of the circle here, remember field points away from a positive charge, so electric field from this would be pointing away, same thing from here, and then electric field due to a negative charge will be pointing towards it, right? So we need to draw those vectors, and we are going to be calculating the magnitude of the vector using Coulomb's law. That's this formula here, KEQ over R squared. If you want to use the main formula along with the unit vector R hat, feel free to do that. If you are using this, remember Q includes the sign, and R hat is a unit vector from the charge to the point. Okay. I just prefer to look at the magnitudes, and then it just becomes a regular vector addition problem, right? So I'll follow this. I'll use the expression for the magnitude, and then I'll go ahead and draw my vectors here. Before that, let me give these some names. This is charge 1, charge 2, and this is charge 3, right? So my electric field at the origin here from charge 1 will be away from it, so it will be pointing away from Q radially outwards, so that would be E1. And similarly, E2 from charge 2 will be pointing away from it. It will have the same magnitude, same charge, same distance, so E2 would be like that. And then E3, electric field from the blue charge here, the negative charge will be towards it. So that will be actually twice as big as that. So that represents my E3. Okay, so I'm going to use this formula to calculate each of the magnitudes. Actually, I just have to do once for E1 or E2 since they are the same. So let me go ahead and substitute my numbers. So E1, that's the magnitude of E1, that's KE, Q divided by R squared. Absolute value of Q is just Q, so that's 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. And then Q is given to be 3 nanocoulombs, so 3 nanocoulombs divided by square of the distance, and the distance is 5 centimeters, so 0.05 meters squared. And when you calculate it, this will come out to be something like 10,788. So I'll write it as 10.788 kilo newtons per coulomb, right? Make sure the units work out, right? Coulomb. So it's newtons per coulomb. And as we have seen, that's also same as the expression for the electric field from Q2. So this is really equal to E2 as well. They have the same magnitudes. And then I have to get E3, which is the magnitude of vector E3, that's KE times absolute value of the charge, which is negative 2Q, divided by R squared. So when you substitute, you can see that it's just going to be twice as much, and absolute value of the minus, so you'll just have a positive value, right? So when you calculate it, it will be twice as big, so it will be 21.576 newtons per coulomb. Okay, so we have all the magnitudes now, and we also see that these directions here, E1 is pointing 30 degrees below the x-axis, E2 is 30 degrees below the negative x-axis, and E3 is completely downward, right? So if I write these in the ij notation, I will have my vector e1, right? So e1 will have a positive x and a negative y. So this is e1 cosine 30 I minus e1 sine 30j, right? Similarly, I can write my e2. e2 is a third quadrant vector, so it's got a negative x and a negative y. So it's got a negative e2 cosine 30i, negative e2 sine 30j. And your e3 is going to be nothing in the x direction, completely in the y direction, so it's a negative minus e3. Okay, so I've got all the vectors expressed in the ij notation, so I just need to add them up to get the total electric field, and when I do that, my resultant electric field is going to be, I'll say E net, which is the vector sum of E1 and E2 and E3. You can see E1 and E2 are the same, right? So these are exactly the same, so they cancel off, so I get a 0i. And then I'm trying to add up all the y's together here. E2 is same as E1. So if I collect all the, I'll say negative j basically, right? Negative j, and that's multiplied by 2 times E1 sine 30 plus E3. Right? So now you just have to substitute the numbers, and there you have it. So this is minus, I'll keep the j for later. When you substitute for E1 from here, right? That's the E1. And then you substitute for E3 from here. And sine 30 is a half. Anyway, if you substitute all this, you end up getting something like 37. It's actually 37,364 or 37.364 j hat. See? So either you can, well, we have to round it to 3 significant figures. So if you want to express it as a vector, you could say E net is equal to negative, well, I have to be careful, the units were kilonewtons per coulomb. Right? So that's negative 37.4 kilonewtons per coulomb j hat, right? So you could either leave it like this, or if anytime they specifically ask for magnitude and direction, you want to go one more step and you say magnitude of the net electric field is 37.4 kilonewtons per coulomb, right? And the direction is negative j hat, or you can say it's completely downward like that. Okay, just a couple of things I realized I missed. There should have been a j hat here. Forgot about that. And also this E3 21 point, this one here, 21.576 kilonewtons per coulomb. And I think the rest of it looks good.